Hey, welcome back, everyone. Today's topic is we're going to be studying how to find the volume of a solid of revolution. And first of all, what is a solid of revolution? Well, I think our best and simplest example that we're all familiar with would be something like this cylinder here. So that's how we're going to start today. I'm going to ask you to find the volume of this cylinder in cubic centimeters. So this cylinder has a circle at each end where the radius is 5 centimeters. And then the distance between the two circles at each end is 12 centimeters. And if you want to pause the video and try and work this out yourself, I encourage you to do so. I'm going to go ahead now and work it out for us here. The common notion for any solid kind of like this is that if I can find the area of the cross section at one end and knowing it's the same cross section throughout, in this case a circle, if I could find the area of that cross section and multiply it by the distance between the ends of that cross section, I'm going to be able to get the volume of the whole thing. And so this time, because the cross sections are circles, the area of a circle is pi times the radius squared. I'm just going to put r squared. And then it's common to call this distance the height, so I'm just going to put h for height there. And now work out the math. Because the radius is 5, this will be 5 squared, and then the height between the two circles is 12. And if you do a quick calculation, this is 25 times 12, and that makes 300. So this is actually 300 pi. And really, we're going to probably leave our answers in terms of pi today. So we're just going to leave this as 300 pi centimeters cubed. Okay, now let's take a look at something here where I actually slice and use numerous of these slices together and actually much thinner ones. Let's take a look at a thinner one first, and from now on, we're going to call this a disc. So here's a much thinner cylinder now turned on its side, and I've highlighted what we call the axis of revolution. And the way you want to picture this today is you can actually generate a little disc like this by actually starting with a rectangle and spinning that rectangle around its axis, around an axis. The axis would be the bottom edge of that rectangle. So picture that rectangle spinning around that line, and the silhouetted image is that little disc. And so we're now going to write this again as the volume being pi times the radius of that disc squared. And they're using the little distance w there, probably for width. That was previously called the height on the cylinder. Now that it's so thin and turned the other way, we're going to call that the width. And notice that the radius is just the distance from the top to bottom of that rectangle. Okay, let's look at an image of a solid where we rotate numerous of these rectangles around and get a much more interesting little solid here. So here we go. Now I've got an image of a region in a coordinate plane, and we've seen this kind of thing before, stacking a series of rectangles inside it. Now we've used a picture like this to estimate the area under the curve between the curve and the x-axis. Well, watch what we're going to do today. We're going to turn this xy plane a little bit on its side. So now this is kind of forming 3 dimensions. And you notice now, watch what's going to happen. We're going to spin all those rectangles around that x-axis. Each one makes its little disc. And so as a sum total, we have a 3-dimensional solid. Kind of looks like a little cup. Okay, and now it would smooth out considerably if I added and subdivided this into more discs. So for now, I'm just going to divide that into 18. I'm going to double the number of discs. And it smooths out considerably into that starting to look like a solid here. Okay, I can still rotate that around, but I want you to key in on the fact that it all started with the graph of that function, the x-axis, and all those little rectangles stacked in there, and they all just rotated around the x-axis. So Those are all little disks. The radius of each disk was the distance from this, in this case, the x-axis, because that was the axis we rotated around. And the distance from there to the graph of the function formed the radius of each of those disks. And you notice that the radius increased as we went from left to right because the function was increasing. So the process of stacking all those rectangles together, rotating them all around an axis to form little disks, and the process of adding all of those volumes together is what integration is going to do. So we're going to take a minute and develop the integration method for this process. Let's go back to our slides and take a look at the process, starting with, again, the process of rotating a single rectangle around an axis. Today, we'll always be rotating around either the x-axis or in some cases the y-axis. And our region that we're going to rotate, or that we're going to put our rectangles in, will be right up against the axis we're rotating around. And so the pre-calculus notion here, or the formula for the disks, was pi times the radius squared times the width. And now in a graphical sense here, the width is the change in x across that rectangle. Now, as you saw a minute ago, within that region, we're actually going to stack numerous rectangles and rotate them all. And so here's where I would be adding up all of those disks. Each one has a radius. And so pi times each of those radius squared times the thickness of each rectangle. And then summing them all together, that would give us the sum total of all of these disks all at the same time. And as we let the number of slices increase, the shape smooths out and we end up finding the entire volume of our solid, and that's going to turn into this integration formula. So notice that the integration formula comes directly from the disk volume formula, pi times the radius squared times the width, and that's exactly what's happening in this integral. I've got pi times the radius squared times the width. Notice the radius is a function of x, because as we slide across this region in the x direction, the radius will change. The most common way we measure the radius is just from the function defining the outline and just measure straight down to the x-axis, and that is going to be your radius. So whatever this function is usually going to be the thing we measure the radius with. Now, as I mentioned a minute ago, we might be rotating around the x-axis, in which our integral looks like the one we just saw, pi times the radius squared dx, because the radius is measured in the y direction and it depends on x. Okay, so as you choose your x on the x-axis and you measure up, that function defines the radius of each of those disks. Now, I could rotate around the y-axis, in which case we choose the y value and then we measure the x. And so we would need a function, x equals a function of y, to measure across the region, and then we're going to rotate around the y-axis. We're going to do one example of each here. We're going to start with rotating around the x-axis. Okay, so again, I want to point out that the integral template really is just based on that cylinder or that disk. The volume is pi times the radius squared times the width of the disk. And the integral is just going to be adding them all together. Okay, so I've actually drawn a picture of what we want to rotate today. And this is the graph y equals root x. I'm just going to actually highlight them here. The curve is y equals root x. I've got the vertical line x equals 4, and I've got the y-axis, or sorry, the x-axis here, which is y equals 0. And so we're going to be rotating this around the x-axis, and what I like to do is kind of put a little swirl around the x-axis. And to note that's we're going to rotate around, and at least one time throughout this region, I like to draw one of those little rectangles that will be rotated to form the little disks. So here's my representative little rectangle. So now picture that rectangle rotating around the x-axis and forming those disks. Okay, so I'm going to do my best to draw that. And so notice that the radius of that disk is the distance from the x-axis to this function. So the first thing we need to do is recognize how we're going to measure the radius. So no matter where I place that rectangle, the distance from the top to bottom of that rectangle is the distance from the function root x to y equals 0. And so I'm just going to write that as a subtraction problem. The distance from root x to 0, or just root x, is the radius of those disks. And this region stretches from x equals 0 to x equals 4. And so those become the limits of this integral. And remember, the template is pi times the integral a to b, radius as a function of x squared dx. And all we're going to do is fill in root x for the radius function. So this is going to be pi integral from 0 to 4 root x squared dx. Now, quite often integrations involving square roots are complicated, but not in this case, because we're going to be squaring that square root. And so this is actually probably one of the easiest volumes you'll ever calculate. This is going to be integral 0 to 4 of just x dx. And here's a good example of one where we should be able to get an exact answer without a calculator. The antiderivative of x is 1/2 x squared. So I'm going to be taking pi times 1/2 x squared between the values 0 and 4. That's x squared. And so plugging in the 4 is going to be 16. 16 times 1/2 is 8. And then plugging in 0 is going to be 0 squared times 1/2 is 0. And so my final volume is simply 8 pi. Noticing we're just going to leave the answer in terms of pi, and there's no units to use here, so my answer is just going to be numerically the value is 8 pi. On example 2, the second one we're going to do, we're actually going to rotate this one 2 different ways. First time we're going to rotate this region between 9 minus x squared. Let me change the color for you. Y equals 9 minus x squared. And then here's y equals 0. And then in the description of the problem, it says we're only going to draw a shade in quadrant 1. So I've used the y-axis as a boundary as well. And for part A, we're going to rotate around the x-axis again. So my axis of revolution is the x-axis. And if I were to draw maybe the rectangle that would form one of my disks, I might maybe just choose to draw it right here. And remember, that disk, that rectangle is going to rotate around the x-axis and make this disk right there. And the radius of that disk is the height of that rectangle, which is just the height of the function 9 minus x squared. So in setup A, to rotate around the x-axis, the radius is a function of x, and it is simply 9 minus x squared. And the interval goes from 0 to 3. And so the volume of that solid is going to be pi, integral from 0 to 3, then the radius 9 minus x squared. Now this integral could be evaluated also just by squaring out this integrand. I could multiply 9 minus x squared times 9 minus x squared, and then find my antiderivative and plug in the 0 and the 3. And I'm going to leave that for you guys to do. I'm mainly going to concentrate on this slide and just the setup of the integral that's needed. So this would be your integral that you have to solve in order to get the volume. I'm going to concentrate now on the second situation, where we're going to take the same region, but we're going to rotate around the y-axis. Let me just erase the disks that we had from the first setup so they don't get in the way. And let's now picture rotating around the y-axis this time. Okay, so that means that my rectangles now get drawn by picking a y value and making a tiny little rectangle this way. And then the disks come around the y-axis this way. Okay, so now the radius is measured there. And notice this time, this has to be a function of x. Okay, so I've got to solve my equation for x here. And so instead of y equals 9 minus x squared, let's first write it x squared equals 9 minus y. And because I'm in quadrant 1, where the x's are positive, I will only need to write this as x equals the positive square root of 9 minus y. And then the distance from that function back to x equals 0 is going to be the radius. And so let me just change pen colors again. This time the radius is a function of y, and it is the distance from that equation, square root of 9 minus y, back to the y-axis, which is x equals 0. And so just the square root of 9 minus y is all we have. And in the y direction, we're going from y equals 0 up to the top of this parabola, which is at y equals 9. And so this integral is in the y direction from 0 to 9. The radius was the square root of 9 minus y. And don't forget, it's going to be radius squared dy. And this one simplifies pretty nice too, because the square root and the squaring remove. So actually, I just said that, but didn't write it. So we need to erase the square root now. And it is now just the integral of 9 minus y dy from 0 to 9. A nice one, easy one to do without a calculator. Today on your exercises, you've got a couple where I expect you to solve the integral without your calculator. This would be a good example of that, because once you have it set up, it is very nice and easy to solve. There's a couple where after you do the setup, you're going to just punch the integral into your calculator and come up with the answer. I encourage you to type in the integral, but not the pi symbol. Let's just leave the answer as a number times pi. Hope this helps you guys. Please get in touch with me by email, or let me know if you have any other questions, or if I need to show you some other examples or point you to some other helpers. Okay, we'll see you back here on Monday.